What a difference a small change can make. Welcome to this quick hits video. My name is Kevin Fiesel and I'm the proprietor of Galaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. Today's video is going to be a ripped from the headlines video, an instance of sorting out an issue that a customer had. This is an example of how a quick code change can make a big impact. This is a quick hits video, so I'm not going to spend a lot of time chatting here. Instead, let's get straight to the demo. Here we are in Azure Data Studio. To set the story, I'm going to create a table. This table is a simple one with just two columns, a var binary value and a string. I've also added a primary key and clustered index on the value just to make life easier. I have also populated this table with 100 million records. That way, you don't have to sit here for a couple of minutes waiting for all of the records to load. And by the way, let's talk briefly about how I generated 100 million rows. It starts with a common table expression and building out 10 rows. If you cross-join E1 with itself, you get 100 rows, giving us 10 to the power of 2, or 10E2. Cross-join E2 and you get 10E4, or 10,000 rows. And if you do that again, you will get 10E8, or 100 million rows. From there, I generated a unique ascending key for each record. Finally, I can insert the row number and a string variant of the row number into the example table. Let's quickly take a look at some data. I'll show you 10 records from this table. We can see that we do have a binary value for SumVal. If I order the table by SumVal ascending, we can see that we have a nice ordering. And I can even sort this by SumVal descending and see that it's still working the way that we would expect. At this point, let me explain what this query is supposed to do. I should also say that this was a third-party vendor query and not the fault of the development team. Regardless, here's what's going on. We need to get the largest value of SumVal in this table, but we also need it to be a big int. The original code performed the following operation. We cast SumVal to a big int, and then get the largest value. If I run this, it takes a moment and then returns me the value 100 million, which is correct. But notice that it wasn't instantaneous. We are just looking for the last value in the table based on our primary key and clustered index, so this should not take long at all. Now, I'm sure that many of you have already caught on to what's happening, but let me explain it in a little more detail. The cast operation is converting SumVal to a different data type before we run max. Thus, we need to scan through all 100 million rows, converting the value to a big int before we figure out the largest value. But there is a trick that I can use. The numeric values we inserted were all natural numbers. We started at 1 and ensured that all values are positive. In this case, there is a monotonic transformation from the binary representation that SQL Server uses for these values and their integer representation. In other words, as my numeric values increase, the binary representations also increase. There is no chance we have a pair of values in which the binary representation order is different from the numeric representation order. Thus, I can swap out the max and cast operations because I don't need to convert each value. Let's run that here just to make sure that it works. And it does, returning 100 million. But that's not enough. No, I want to check the performance difference between these two. And for that, I'll use SQL Sentry Plan Explorer. There haven't been many changes to the product since SolarWinds bought Sentry 1 a couple of years ago, but it is still the best product out there for performance analysis in SQL Server. Anyhow, I have my two queries in a plan window. Let's select Get Actual Plan and generate some plans. And immediately we can see that the first version of the query is taking a little bit of time. Then we get the updated version of the query and, well, we can see the difference here, and it is a huge one. The first version of the query performs a clustered index scan, bringing in 100 million rows and performing a compute scalar operation to convert to a numeric value. Then we perform a hash match aggregation, figuring out which is the largest value. It's a hash match because the optimizer is parallelizing this query, basically sending a group of values to each CPU core and saying, tell me which of these is the biggest. Then, given the maximum of each subgroup, we take the largest value among those subgroups and return it to the user. It's a very efficient strategy if you have multiple cores and the need to work with each row in the data. But it turns out that we don't need to work with each row in the data. If I switch over to the second query, we have a clustered index scan and a top operator. We are reading one page, getting the largest value from that page. We still have a stream aggregate here because we are performing a max function call. Finally, we need a compute scalar to take that one row and turn it into a big int before returning it to the user. You might be thinking to yourself, hey, this is a silly example, but this kind of thing happens very frequently, especially as data sizes grow organically. A solution that worked well enough in development against 10,000 rows turns into a mess at larger volumes, and we can cover up a lot of sin with hardware. In practice, this query takes under a second, so unless you think about it or review the query store data, you probably won't even notice the waste of resources. In my customer's case, this was a query that happened hundreds of thousands of times per day. We were able to save about 14,000 CPU seconds per day and roughly 1,500 wall clock seconds per day. Along the way, we reduced logical reads from 3 billion per day to under 300,000. All of this with a one-line code change from a third-party vendor, which that's not bad for a day's work. But before we go, there is one important caveat. I mentioned that natural numbers are monotonically increasing, and that is true. But what happens if we introduce a negative number into the mix? Let's try that now. Then we'll run the original code and the alternate version. And this time, after we finish running, we can see that, well, there is a difference. The reason for this is that negative numeric values in SQL Server start with F and will always be greater than positive values. It's the clever mechanism that computer designers use to support positive and negative values in a fixed number of bytes, and it will cause a problem if you ever insert a negative number into this table. So keep that in mind. If you're dealing with negative numbers, you might have to get clever with the where clause and add a filter where your value is less than 0xf. That is going to do it for this quick hits video. This was a short video, but I wanted to illustrate the importance of order of functional operations. A small change can sometimes make a big difference. We'll have links and show notes in the description below. And until we see each other in the next video, take care.